Okay, all right, welcome back. Today we will continue what we learned last time. Um, okay, let's first recall what we did last time. Okay, last time we actually started the chapter 3, applications of derivatives. Um, in this chapter, we will use derivatives to study the maximum and minimum of a function, i.e. the optimization problems. I think the first in chapter 3.1, we actually introduced the maximum and minimum values. Definition of maximum and minimum, i.e., if we have a maximum, if we have maximum if the value locally greater than any other function values, and similarly we have a local minimum. And then we have global maximum, global minimum. Now, of course, global maximum is obtained by comparing local maximum. The maximum among local maximum gives us global maximum. The maximum among local minimum, the minimum among the local minimum gives us global minimum. I think all these maximum and minimum values are called extreme values. Then we actually have the existing theorem of extreme value theorem, which says if a function is continuous on closed interval, then the closed interval should be finite. Then fx has absolute maximum and minimum on this closed interval a to b at some point c or d. So we can actually, in this situation, continuous function on closed interval, they do achieve a maximum and minimum. So in this, and then we have the Fermat theorem, which says if a function has local max and local min, and then derivative exists at c, then the derivative necessarily vanishes at local max or local min. So this is what we did last time. Okay, now this to find maximum, local maximum, or local min, it is suffice to the following. We give a definition. If C is called a critical number of f, C is called a critical number of f of fx. If fc derivative at c vanishes, or f derivative at c does not exist. Now, of course, this c should lies in the domain of the function f. Okay. Now, Fermat theorem tells us a condition that at local maximum, if derivative exists, then derivative should vanishes. Now, from Fermat theorem, actually, Fermat theorem tells us what kind of location that actually we can look for local max or local min, i.e., we should look for local max and local min at exactly critical numbers. Okay, so at the critical numbers, let's see some example. Give some example of critical numbers. Let's see this example. Fx equal to x cubed plus x squared minus x. Find critical numbers. Of fx. Okay, now, so this function fx is a polynomial, so f derivative always exists. So it's differentiable everywhere. Now we take derivative by power rule. Now derivative of x cubed, we get a 3x squared. Derivative of x squared, we get a twice x. Derivative of -1, we get this. Derivative negative x, we get -1. Then we actually factor this. This should be 3x minus 1, x plus 1. So after to find critical numbers, so we need to find, we let f derivative be 0. Then we get 3x minus 1 x plus 1 is 0. And then we from the product is 0 if only if one of the factor should be 0. Okay. Then we get the solution x equals 1/3 or x is -1. So we have two critical numbers. Okay, critical numbers. Critical numbers. Critical numbers of fx is we have two critical numbers. -1. Sorry, it's positive 1/3. Okay. Okay. So now the key is we should look for given a continuous function, giving a continuous function, fx on a to b. We should look for to find its maximum, all its local max or local min, all local max or local min. So we should look for local max. We should look for local max or local min at critical numbers. Critical numbers of f within this a to b. Belongs to a to b. Okay. Okay, all right. Now, actually, we have the closed interval method. So we have the closed interval method to find the global maximum, global maximum. Then, Fermat theorem tells us what kind of location that we look for maximum, local minimum. And then once we find all possible local max and local min, and then we compare local max and local min so that we can find global max and global min. So this gives us the closed interval method. Which says the following. Interval method. Now to find absolute max and absolute minimum of a continuous function on a closed interval. Okay. To find the absolute max or an absolute min of a continuous function fx, on a closed interval, a to b. Do the following. First step, differentiate the derivatives. First step, find all critical numbers. Critical numbers of fx on open interval a to b. Now for the boundary, we will look for its value. We will find its value. So we don't need the critical numbers at the boundary. Now find so the next step. From Fermat theorem, we know that the local max, local min actually occurs at the critical numbers. Okay, so we just compare all the function values at critical numbers. Now be careful. At some critical number, it may not be local max or local min. Okay, but it's local max and local min should appear at these critical numbers. So we just compare all the function values at these critical numbers. So the second step, find all the function values, all the function values function values of f at all critical numbers. All critical numbers. Critical numbers. Critical numbers. And also for the boundary, we do we find also the function value at the boundary. Okay, and then 3. Now this actually gives all possible cases of local max and local min. So the function values in 2 is actually contains all the local max and local min. Okay, all the local max and local min. Now and then from 2, we just compare all the numbers, all the function values from step 3. Then this including all the local max and local min. If we compare them, then the maximum of local max gives us the global maximum. Okay, so the maximum, the maximum of function values of the values in step 2. In step 2, gives us the absolute maximum. The absolute maximum of f on AB. And similarly, the minimum. Sorry. Okay. The minimum of the values in step 2 gives us the global absolute minimum of f on A to B. Okay, so this closed interval method is actually really important. So it gives us a method that compute absolute maximum and absolute minimum. Okay. Now let's see some example. Let's see this example. Find the absolute max, absolute mean, and absolute min of the function fx. Let's see this. Fx be x cubed minus 6x squared plus 5 on the interval. Let's see, for instance, -3 to 5. Okay, now this degree three equation. So this degree 3 polynomial, we don't know how to find its maximum or minimum from what we learned right before. Now actually we know degree 2. Okay. Now degree 3, actually we can deal with by the method that we learned today, i.e. closed interval method. So we use closed interval method to find its absolute maximum and absolute minimum. Now the first step, find all critical numbers. So let's find critical numbers. So first take a derivative. So derivative, we get use power rule. So x cubed gives us derivative 3x squared. Now this gives us now 5 derivative gives us 0. So this is actually factor out the 3x. So this 3x, x minus 4. So to find critical numbers, so we said, so this derivative exists everywhere. So we set derivative to be 0, set f derivative to be 0. So we get 3x, x minus 4 is 0. So we find x 0 or x is 4. So we have two roots. So two critical numbers. We get two critical numbers. Critical numbers. 0 and negative 0 and 4. 0 and 4. So we should look for by the closed interval method. We should look for the function value as critical numbers, and don't forget the boundary. Don't forget the boundary. Don't forget the boundary. Okay. Okay. So we have the boundary. So f-3, f5. The two boundary value -3 and 5. Okay. And then the two critical numbers f0, f4. Okay. Now here is tedious. Now we just plug in the numbers. Plug in the numbers. So f-3, you plug in -3, you get a -3 cube -6 -3x squared plus 5. And then finally you see this is just a little bit of computation by algebra. So we just skip it. f0, you plug in 0. Plug in 0. So we get a 5. f4, you plug in 4. And this you get -27. So you can use an algebra package, or you use a calculator. And also it's not that bad to compute by hand. Actually, you got this -20. And then you compare. Then you compare all the numbers. Compare all the numbers from the right. Then you see we have the minimum. So you see -76 gives us absolute minimum. And this 5, the value 5 gives us absolute maximum. Okay, maximum. So we have fx. So finally we can conclude that fx attains absolute minimum -76 at x equals -3, and then attains absolute maximum 5 at x equals 0. Now, of course, this is we are considering the function value on the closed interval -3 to 5. Okay, -3 to 5. Okay, one more example. Let's see this example. fx is x 3x⁴ minus 4x cubed minus 12x squared plus 1. I think this closed interval is -2 to 3. Well, what we do is we use closed interval method, the closed interval method, to find its maximum and the minimum. Okay. Now what we do is we first step of closed interval method, I find all the critical numbers of f. To find critical numbers, so we first take derivatives. Take a derivative of f. Use power rule. Now each term, as actually we get the derivative for term-wise derivative. So 3x⁴, then we get 3 times 4x cubed. Take a derivative. And then 4x cubed, we get 4 times 3x squared. Now 12, we get 12 times 2x. Now 1, we get a 0. So this will be 12x cubed minus 12x squared minus 24x. So we have common factor 12x. Now we factor out the common factor 12x. And what is remaining is x squared. And the second term, we get x remaining. And then finally, the last term, we get -2. And actually, we can factor this quadratic. Then what we get is x minus 2, x plus 1. Okay, then we find critical numbers. So the derivative exists everywhere, so it's differentiable everywhere. So to find critical numbers, it is suffice to find where the derivative minus is. So we set f derivative to be 0. Then we get 12x x minus 2 x plus 1 is 0. So we get 3, we have 3 factors. So actually we get x is 0, the first factor, and then the second factor x minus 2 to be 0, then we get a 2. Then x plus 1 to be 0, then we get the factor negative 1. So we have 3 roots, 3 solutions. Then we find the 3 critical numbers. So we have the 3 critical numbers. So all these 3 are the critical numbers. Okay, all these are the critical numbers. So critical numbers. Okay, so we have 3 critical numbers. Don't forget the boundary. So we should look for the values. The boundary. So remember what we are talking about. The interval is negative 2 to 3. So we should look for f. So arrange this numbers in order. So it's negative 2, f negative 1, f 0, f 2, f 3. Okay. Now here it's better to use algebra package. Now you can use seed or use algebra. Plug in the function, plug in x by negative 2. So we will not compute by hand here. We will just directly, so it's not enlightening. So we just give you the result. You can use check user calculator. So here f negative 2 we get 33. F negative 1 plug in negative 1 we get a negative 4. F 0 we get a 1. F 2 we get negative 31. F 3 we get a 28. And then we compare all the values. Then we see we have absolute maximum. You see, we compare all the values here on the right. So this 33 gives us absolute or global max. And then this negative 31 gives us the minimum. Okay, absolute minimum. Okay, then we are done for this problem. So at the function value, the function achieves maximum 33 at negative 2 and achieves absolute minimum at 2. The minimum is negative 31. Then we're done for this problem. All right, let's see another problem. Okay, example. Let's see this example. F theta is cosine theta plus sine squared theta, where theta is everywhere. Theta is defined for all real numbers. Okay. Okay, find the maximum and the minimum. Find the max, the maximum, and the minimum. Max and min of f theta. Okay, what we do is we change the variable. Here we have sine theta, we have cosine theta. Then what we do is we have a relation between sine and cosine. Remember, sine squared plus cosine squared is 1. Okay, so we first step we substitute sine squared by so we solve sine squared, which is 1 minus cosine squared. So that here we only have cosine. Okay, so we only have cosine. Then we actually change the variable. So let t be cosine theta. Now remember, the cosine theta, the range of cosine theta is from negative 1 to 1. So here t is in negative 1 to positive 1. So and then f. So we consider then the function will be gt. We replace cosine by t. plus y minus t squared. Okay, plus y minus t squared. Here t is in -1 to 1. Okay, so actually f theta equals dt. So it suffices to find the maximum and minimum of the function g. Okay, of the function g, gt. In this closed interval -1 to 1. So what we do is we use closed interval method to find the maximum and minimum. So what we do is use closed interval method. So we find g derivative, find correct number, g derivative of t. Now t derivative gives us 1, 1 derivative gives 0. Now t squared gives us 2t power, so which is the y minus 2t. So this is a polynomial, so its derivative exists everywhere, so it's differentiable everywhere. So to find the critical numbers, we only need to solve the case that g actually, so we set g derivative 1 is 2 is 0. Then we get y minus 2t is 0. And then we solve for t. It's very easy. 1 equal to 2t. So which means t is actually a half. Then we find, so what we need to check to compare is the three function values. So the boundary, g -1, g a half, and g1. Okay, now we plug in 1, g -1. So let t, substitute t by -1. So it's easy to compute by hand. It's -1 plus y minus -1 squared. So this is not bad, it's -1. Now g 1/2, so it's plugging t by 1/2. So 1/2 plus 1 minus 1/2 squared. So this will be y minus a quarter plus 1/2. So it's y/2 plus 3/4. So it's 5/4. So g1 will be plugging y, 1 plus y minus 1 squared. So it will be 2 minus 1, so it's the y. So we compare the values. -1, y, and 5/4. So we get gt attains maximum, global maximum, absolute maximum at t equal to 1/2. Global maximum is 5/4, and g attains minimum, absolute minimum at t equal to -1. The global minimum is -1. Okay, now let's, we need to solve for theta. So f theta attains absolute maximum. Also the same absolute maximum when, remember, t is cosine theta by our substitution, when cosine theta equals to 1/2, i.e. theta be, now from cosine theta is 1/2, we can solve for theta. Theta is actually plus minus pi over 3. Okay, plus minus pi over 3 plus 2 n pi is periodic. Okay, plus 2 n pi. Okay, now f theta attains to find the absolute minimum. Also -1 when cosine theta is, now it achieves for g, the function gt attains absolute minimum when t is -1. So we let cosine theta to be -1. Then actually we know theta is actually, i.e. when theta is odd multiple of pi, pi plus periodic 2 n pi, because here theta is periodic, so it's a odd power, 1 plus 2n multiple of pi. So here n is integer, can be any integer, n is any integer. Okay, then we are done for this problem. Okay. Okay. Let's see more examples. More examples. More examples. Let's see this example. Example. Let's see this example. Fx to be log x over x. Here x is in 1 to 3. In 1 to 3, the closed interval. Okay. Now we actually use the closed interval method. The first step, find its critical numbers. Find its critical numbers. Now, critical numbers. So we first take derivatives. Take a derivative of f. So this is log x over x. Okay, now we use quotient rule. Quotient rule, x squared. Now log x derivative times x minus log x keep it fixed, multiply x derivative. So quotient rule. So what we did use quotient rule. Quotient rule. Okay, quotient rule. Then we find the derivative. Use quotient rule. So log x derivative. Log x derivative. What do we get for log x derivative is now logarithmic differentiation. So we get a flip the input minus x derivative is 1. Okay, 1 over x times x. So we get actually 1 minus log x squared. Then we find all the critical numbers. All the critical numbers. So it we are actually talking about the value we are talking about is -1 to 3. So the critical numbers. So the denominator is never 0. So all the critical numbers should be so it's differentiable. So we set the derivative vanishes. So we get 1 minus log x over x squared is 0. So this is 0. The fraction is 0 if only if the numerator is actually 0. So this actually tells us log x is 1. And then we solve for x. X is actually e. Remember the value of e, the base of a natural log. The base of a natural log is, remember, 2.718. You can write down several digits, etc., etc. So it's lies in between 1 and 3. Lies in between 1 and 3. So, so the critical number. So we have only one critical number, i.e., the critical number is the base of a natural log. So by the closed interval method, step 3, then we actually compute 3 values, fe and f3. Okay. Now f1, we plug in f1. Now remember fx is log x over x. f1 we got log 1 over 1. Remember log 1 is 0, so it's actually 0. Now fe, we get log of e over e. Log e is 1, so it's 1 over e. 1 over e. Okay, 1 over e. Now what is f3? f3 is log 3 over 3 squared. Okay. So now how do you compare 1 over e and 1 over e and this log 3 over 3 squared? Now you better use a calculator. Now actually do we have some actually we can do better use without a calculator we can still solve this problem. But actually we need a little more knowledge if we without a calculator. Now this can be done by later sections. So the idea is we know that the function is If its derivative is negative, then we know the function is actually degrading. If the derivative is positive, the slope is positive, i.e. the function is actually increasing. So actually we can use this kind of information to work on this problem. So here the derivative, we can actually see the derivative of f is actually positive from 1 to e. So it's increasing from 1 to e. It's decreasing from e to 3. Actually this gives us the maximum. This gives us the maximum. This gives us the minimum. This gives us the minimum. Okay, give us fe gives us the maximum. F3 gives us the minimum. Of course, you can compare this user calculator, find the exact value. Or you can estimate a little bit, simply just estimate. The line, remember E is 2.7, it's really close to 3. So line 3 is close to 1. So this is around, so this is around 1 over 3 squared 9. This is the around 1 over 3. Okay. So you see so 1 over E is bigger. 1 over E is bigger. Of course, you can use calculator. Okay. Now more examples. My example, fx to be x times e to the negative x. The interval is 0 to 2. 0 to 2. Okay, we use the closed interval method. What we do is we differentiate. So find critical numbers. The first step, find the critical numbers by differentiation. So now this is the product, so we use product rule. So x derivative multiply e to the x fixed plus x keep it fixed multiplied by e to the negative x derivative. So we apply the product rule. X derivative give us y. E to the negative x by chain rule. E to the x is derivative itself. Don't forget we have composition. So the negative x is inner fraction. So we use chain rule. So this will be e to the negative x minus x e to the x, e to the negative x, sorry. And then we factor out the common factor. So it's e to the negative x y minus x. Now the derivative exists everywhere. The function is differentiable everywhere. So to find the critical numbers, we only need to find the critical numbers when the derivative vanishes. So we set f derivative to be 0. So we get e to the negative x multiply y minus x is 0. Remember, exponential function are never 0. Okay, remember e to the negative x. This is an exponential function. It's never 0. Its value is never 0. So it is suffice. So it is suffice. So we get this factor y minus x to be 0. Then we get x to be actually 1. So we find x value is 1. So this is actually critical numbers. Critical number. 1 is the critical number. Okay, so now we need to find from the closed interval method. What you do is compare the 3 function values. And now f1 is actually f1. Now the boundary, the two boundary of the two boundary, which is 0. Remember the closed interval. The interval is 0 to 2. 0 to 2. Okay, remember the function is fx is x e to the negative x. So we get 0 times e to the negative 0. So this is 0 times anything, we get a 0. f1, then we get 1 times e to the negative 1. So we get 1 over e. Okay, 1 over e. Now f2 is so this is the around 1 over 2.7, 1.8, etc., etc. So f2 is actually 2 times e to the negative 2. So actually we get a 2 over e squared. Now how do we compare? Now this is actually 2 over e squared. You can write as 1 over e times 2 over e. Okay, 2 over e. And you see 2 over e is less than 1. 2 over e is less than 1. Because e is greater than 2. So this is less than 1 over e. Now of course f1, f2 they are positive. f0 is 0. So we actually find the maximum fx attains absolute maximum. The maximum is actually 1 over e at x is 1, and fx attains absolute minimum. The minimum is 0 at x is 0. Now of course we consider the function value within the interval, closed interval 2 to 0, 0 to 2, 0 to 2. Okay. Okay. More examples. Okay. Let's see. Okay. Now, maybe one more example. Ft to be cubic root of t eta minus t, where t is from 0 to 8. All right. Now what we do is we use the closed interval method. So differentiate. So ft. So this is t to the 1/3. 8 minus t. So we distribute this is 8t to the 1/3 minus t to the, t to the 1/3 times t. So we get to add the exponent 1/3 plus 1. So we get a t to the power of 3 over 4 over 3. Now differentiate. So we get 8t 1/3 derivative minus t to the power this derivative. Now we get this is the power rule. 1/3 times t to the negative 2/3 minus 4 over 3 times t to the 4 over 3 minus 1, 1/3. Okay, so this will be, what do we get actually? Now this we get, we factor out the common factor, so this is the 8 over 3. 1 over t to the 2 over 3 minus 4 over 3 t to the 1/3. Okay, so we do this. So we factor out the 4 over 3 t to the negative 2 over 3. Then the first factor will be 2. The second factor will be actually t. It's not easy. It's not difficult to check this. It's not by algebra. Now we need to be a little careful. Now to find the critical numbers. So we have trouble when t is 0, because here we have a negative power of t. So critical numbers. So f derivative of t is not defined, is undefined. As t, it will be 0. So we have one critical number which is 0. So one critical number. Now to find other critical numbers, we set the derivative vanishes. We set the derivative to be 0. F derivative at t 0. So we get 4 over 3 t to the negative power 2 minus t to be 0. Now remember, t to the negative power is 1 over something. Okay, 1 over a non-zero quantity. So this t to the negative power is non-zero. So we actually get 2 minus t should be 0. This factor. and then we get actually t should be 2. So we find two critical numbers. Two critical numbers. Two critical numbers, i.e. 0 and 2. 0 and 2. So we need to check now. For this problem, the critical number exactly agree with one of the endpoint of the interval. Okay. Now the interval, remember the interval is so 0 to 8. So actually we need to find the function values from the third step, step 3 of a closed interval method. F0. Okay, F0. All the critical number, function value at the critical number. Don't forget the boundary. Don't forget the function value at the boundary. F8. Now remember the function is defined as remember ft is cubic root of t, t minus sorry, it's 8 minus t. The other way around, 8 minus t. Okay, f0 is very easy. Plug in t to be 0. Cubic root of 0, then we get actually 8 minus 0. This is actually 0 times t. F2, we get a cubic root of 2, 8 minus 2. So this we get a 6 times cubic root of 2. Now F8, cubic root of 8. Now 8 minus 8. So it's actually 8 minus 8 is 0. So this is 0. So you see, this is we have the positive, which is absolute max. Now 0, the two boundary values, they are both 0. So we have absolute minimum. So then actually ft attains maximum 6 cubic root of 2. Absolute max. Absolute 6 cubic root of 2 at x t equal to v2. Now ft attains absolute min 0 at t to be 0 and t to be 8. T equals 8. So we have two positions where f attains absolute minimum. Then we are done for this problem. Okay. Now we are done for this section actually. Maximum and minimum values. Okay, all right. Let's go to next section, which is the mean value theorem. The mean value theorem. Now this section actually is really important. The mean value theorem. It's just 3.2. The mean value theorem. Okay, now let's start with rule theorem. Okay, rule theorem says this: if we have a continuous function, if we have a function that satisfies the following conditions, let fx be a function that satisfies three conditions. One, continuous on closed interval, on the closed interval, closed interval A to B. Two, differentiable on open interval, differentiable on the open interval. A to B. Three, the function value at A and B agree. Then the conclusion is there exists a number C in this open interval A to B such that the derivative C vanishes. Such that F derivative C vanishes. So this is the root theorem. Now, the idea of a root theorem is the following. Now, if we plot the picture, now it's differentiable on closed interval, continuous, differentiable on closed interval, open interval, continuous on closed interval. So it looks like this. Suppose it's A, and this is B. So here this is A, this is B. Okay, so the function value is the same at A and B. So the endpoint at the same height, FA equals FB. Okay, at A and B, they have the same height. Now the idea is, on this interval A to B, there should be some maximum and minimum, and this maximum and minimum should be different from A and B. So at some point C, you see we have some maximum. Okay, we have maximum and minimum. So the key idea is fx attains maximum or minimum. So for instance, let's do this. This is A, and this is B. Okay, at A and B, AB, they have the same height. So this suppose is A, this is B. Okay, so at some point C, there should be a maximum or minimum. Okay, so at the maximum minimum, there is tangent line, horizontal tangent line. Okay, horizontal tangent line. Horizontal tangent line means the slope is actually 0. Okay, horizontal tangent line. Horizontal tangent line. Now, the conditions that f is differentiable on open interval actually guarantees the existence of tangent line. Okay, the existence of tangent line. Now, the conclusion says there is a number C in the open interval A to B such that the derivative vanishes. This actually tells us that at the maximum or minimum, we have a horizontal tangent line. Okay, so this is actually what the root theorem says. Okay, this is what actually root theorem says. Now the proof of root theorem is not difficult, and also is, however, we will skip this proof of root theorem. It's really clear if you look at the picture, the geometric picture. Okay, so this is root theorem. Now we actually talk about the mean value theorem. The mean value theorem. Actually, mean value theorem, there are several versions of mean value theorem. Now, the current situation, what we did is actually the Lagrange mean value theorem. Lagrange mean value theorem. So this is the most usually used version of mean value theorem. The Lagrange mean value theorem says this. If let fx be a function that satisfies, let fx be a function that satisfies y, f is differentiable, is continuous on the closed interval. So this is the same as the first condition of root theorem, the first two conditions of root theorem. F is differentiable on the open interval, closed interval A to B, on the open interval, A to B. Now we no longer have condition 3. Actually, Lagrange mean value theorem removed the condition of 3. Condition 3. Then the conclusion. Then there is this number C. A number C in the open interval A to B, such that f derivative C equal to fb minus fa b minus a b minus a, or we write in this manner, or equivalently fb minus fa equals f derivative C times b minus a. Okay, now Lagrange mean value theorem. Let's plot a similar picture for the Lagrange mean value theorem. So now here we no longer have the condition that b, f, the two function value equal or not. We don't know actually. So let's just plot a function looks like this. So suppose this is A, this is B. Okay, this is B. Okay. Okay. Now FB minus FA over B minus A. So what is this thing? So we have this point AFA. We have this point BFB. So this was PQ. Now the 2 points. Now if you compute the slope of the line PQ, actually you will find y minus y over x minus x. So actually the line PQ, so KPQ is actually FB minus FA, y minus y value over x minus x value. Okay, so this we have a line PQ, we have line PQ. Now if you rotate a little bit, now you see the maximum. So this is actually similar to rule theorem. Actually, now if you rotate a little bit, this will be horizontal. So this gives us that the comparison with rule theorem. Okay. Now the derivative at C actually equal to the slope of PQ. Actually says at a certain point C. So the condition says at C, at the point C, FC, the tangent line, you know, the derivative at C equal to the slope of PQ. You know, if two lines are parallel, then we know actually their slopes are the same. Okay. Now the derivative gives us the slope of the tangent line. So derivative at C equal to the K slope of a PQ. This means the tangent line at C, at the point, let's use R. That point is R. That RCFC is parallel to the line PQ, to the line PQ. Okay, to the line PQ, to the line PQ. Now, if you rotate your head a little bit, now this actually is the same thing as rule theorem to make sure it's horizontal. Okay. Now another point of view is actually this. Now, if we choose fx, the function to be position function. Suppose we let f to be position function. Example. Another example. We are talking about st and vt. St, position function. Position function. Position function. From A to B, t from A to B. P from. Suppose we are actually, a particle moves along a straight line. So the position function is given by t, s equal to st. Now, What is this? SB position, change of position gives us displacement. Change over time, B minus A. This gives us the average velocity. Average velocity. Average velocity. Distance over displacement over time, average velocity. Velocity. Now, Lagrange mean value theorem tells us that S derivative at a certain point C equal to SB minus SA, B minus A. Now, this actually derivative tells us velocity, okay? This tells us instantaneous velocity. Instantaneous velocity. Now, this tells us that if a particle moves along a straight line, then from T to be A, from T, A to B, they necessarily at a certain time C, the instantaneous velocity equal to the average velocity. Equal to the average velocity. Okay. Application of mean value theorem. Let's see some application of mean value theorem. Now, from mean value theorem, actually we can we can deduce root theorem actually. So they are actually equivalent. Now, if we have condition 3 in mean value theorem, now remember we only have condition 1 and 2. 1 and 2. Now, if instead we have condition 3, if we have, if FB equal to FA, now we have, F derivative at C equal to FB minus FA over B minus A. Now this will be FB equal to FA, so this is 0 over B minus A. This will be 0. Then we have, now the condition says actually is exactly what the root theorem says, okay? Which is exactly what the root theorem says. Exactly, which is exactly what the root theorem says. What the root theorem? This is exactly the conclusion of root theorem, which is exactly the conclusion. Exactly root theorem. Conclusion of root theorem. So this tells us Lagrange mean value theorem is a special, actually is more general than root theorem. I.e., root theorem is actually a special case of Lagrange mean value theorem. Okay, it's a special case of Lagrange mean value theorem. So we can actually get Lagrange mean value theorem if we assume gives us is more general than root theorem. Now, actually, we prove Lagrange mean value theorem by root theorem. Now, we prove Lagrange mean value theorem by root theorem. Root theorem. We prove Lagrange mean value theorem by Lagrange mean value theorem by root theorem. Prove Lagrange mean value theorem. Okay, from Lagrange mean value theorem, you see, we can prove root theorem by just setting FB equal to FA. Then we get the conclusion of root theorem. Now, actually, conversely, this is also true. We can prove Lagrange mean value theorem from root theorem. What do we do? The key idea is how do we prove Lagrange mean value theorem? Remember, in Lagrange mean value theorem, FB and FA, they are different. Okay, they are different. The key idea is actually we try to subtract certain things such that the function value will be equal at the two points at B and A. They actually equal. Now you see FB and FA, they differ by by certain quantity. What we do is we subtract certain height. Okay, the height is actually changing from A to B. Now the height we subtract at A is 0, and then the height at B we subtract is actually determined by certain thing. So we subtract. Now what we subtract is actually the line equation. Okay. So the key idea, let me just plot it here. Plot it here. Okay. So suppose it's FA, FB. Let me put it here. It's FA, we have B. Okay. What we subtract is actually the line equation. The tangent line equation, the line equation. Okay, this line equation L. We can write down the line equation L. L is actually y minus FB equals now the slope is FB minus FA, B minus A, X minus B. Okay, so what we subtract is actually this quantity. We subtract this quantity. So y will be FB plus starting quantity. Let's subtract this. X minus B. Okay, what we subtract actually is let prove. Okay. Let's do this. Let the capital F be this. Let capital X be little f. Subtract this function. So we let height fx be fb minus fb minus fa b minus a x minus b. Okay, this is the height function. We subtract the height function, then you see, then what we actually get. Now, actually, FB equal to FA anymore. So we've actually checked FB equal to FA. Check that. So again, height function is a polynomial, so it's differentiable everywhere, and it's continuous everywhere. So this capital F satisfies is continuous. Satisfies 1, 2 is continuous. Continuous on closing of A to B. Fx is differentiable on opening of A to B. Differentiable on opening of A to B. Then we actually, now this condition is 3. We actually, of course, we should have this 3. 1, 2, 3. Capital FA equal to capital FB. The reason is we already subtract the height such that capital FA equal to capital FB. Okay. The two endpoints have the same height by our subtracting. We subtract the certain height. Then we can actually you check this. And then we can actually get rule theorem. Rule theorem gives us by rule theorem. There exists number C. Exists C in A to B, such that the function f derivative at C vanishes. Now you check f, capital F is little f minus hf, hx. Now capital F derivative is f derivative x minus h derivative. Now h derivative, now you can read, H derivative gives us the slope of the line. Okay, this is actually f derivative x minus is constant. Derivative h is constant, so this is actually fb minus fa, b minus a. So we get a 0 equal to capital derivative at c. Capital F derivative at c equal to capital F plugging x by c. Okay, then we finally get f derivative at c. Now move the terms to the left. Then we actually get f derivative at c equal to fb minus fa minus b minus over b minus a. So which is exactly the conclusion of Lagrange unit theorem. This proves the Lagrange. So this proves proves Lagrange mean value theorem. The Lagrange mean value theorem. The Lagrange mean value theorem. Then we are done for Lagrange mean value theorem. Okay. Okay, let's see some applications of Rolle theorem and Lagrange mean value theorem. Let's see some applications. Example. So that the equation x cubed plus x minus 1 has exactly one real root. One real root. Okay, now here don't take care about the number real, the word real root. Now the conclusion will be different if you study actually complex number, complex number. Okay. Now what we do is we use proof by contradiction. Now suppose proof. First of all, we know actually it has one root. Why? Actually, this is true for any odd polynomial, odd degree polynomial, because for odd degree, you see, if x approaches positive infinity, the function value is actually positive infinity. So let fx to be x cubed plus x minus 1. Then actually, as limit fx as x approaches infinity, this is actually infinity. Limit x approaches negative infinity, this easily check, this we get negative infinity. Why we get negative infinity? Because the highest degree is odd power. So actually odd power of a negative number is negative. So this is why is actually we get negative infinity. So somehow the function value should change from negative to positive. So then they guarantee a solution, okay, by continuity, by intermediate value theorem. So actually we know that's the root. Okay. So by intermediate value theorem, there exists number C. A number C, a number C, maybe C, such that f C is 0. Okay, it changed from negative to positive. Okay, this is true for any odd polynomial, odd degree polynomial. Odd polynomial, there's always a real root. Okay, from this argument. Okay, now actually we can now you can actually get more information. For instance, you find f0, you plug in 0. 0 cubed plus 0 minus 1, which is a negative 1, which is less than 0. f1, you plug in 1. 1 cubed plus 1 minus 1, which is 1. Positive. Actually, from 0 to 1, it changes sign. From 0 to 1. 0 is negative 1, 1 is positive 1. If you plot, this is the next intersection. Okay, intersection. Such that derivative, the solution, x0, let's use x0. Then by IVT, intermediate value theorem, there exists a number x0 in 0 to 1, such that f0 is 0. Now, actually, we know that exactly there is one real root. That is the one real root. Now, we need to show that actually it cannot have more real roots. Now, okay. Yeah, the key idea is if we assume there are two roots, then actually it satisfies the condition of root theorem. Such that we can conclude that by root theorem the derivative vanishes. Now, however, if you take a derivative for this f, now let me finish this. Suppose there are two roots. Then suppose there are two real roots, fx0 equal to fx1 equal to 0, two roots. Then you can get f derivative at c vanishes by root theorem. So we have condition 3. This is condition 3. Condition 3. Now condition 1 and 2 is automatically satisfied because it's polynomial. By root theorem, f derivative c by root theorem. Now, however, f derivative x, you take power, take the derivative 3x squared plus 1, which is never 0 because it's positive number. 3x squared is positive, plus 1 is positive, which is the condition. So f derivative c cannot be 0. So which is contradiction. So this contradiction shows that cannot be two more zeros. So this shows f cannot have two or more or two real roots. Now we actually know it has one real root. So this means fx has exactly one real root. Has exactly one real root. Now, how to find the real root from, we know it's lies in between 0 and 1. Now, how to find it? Actually, we will, in later section, once we have Newton's method, we will talk about how to find actually the roots numerically. Okay. Let me just stop here for today and continue next week on Monday. I will assign homework problem on website. Just check your website. Okay. Okay, let me stop here for today. I will see you on Monday.